All right, folks, we are back in our FBI suits to re-question a victim that was focused only on the entropy of the system. Now, spinning the block and going back to what we learned about the second law of thermodynamics and entropy, we know that entropy of the system was not the only necessary part for determining reaction spontaneity. We needed the change in entropy of the system and the change in entropy of the surroundings to get the change in entropy of the universe for the second law. And we needed it all to be greater than zero to ensure spontaneity. The second law of thermodynamics also dictated that a decrease in the entropy of the system is going to be outweighed by an increase in the entropy of the surroundings during a spontaneous process. All of this again so that the delta S of the universe remains greater than zero. We can also use the second law and then add in the layer of information we know about standard states and say delta S naught of the universe is equal to delta S naught of the system plus delta S naught of the surroundings. And even in our standard states, all of it needs to be greater than zero. So far, we've spent all of our time examining the change and entropy of the system. Now we get to examine the influence of the surroundings on the total entropy change. And by measuring both the delta S of the system and the delta S of the surroundings, we can predict finally whether a reaction will be spontaneous at a particular temperature and therefore go towards spontaneous change. We finally get to figure out the premise of our overall hunt. But first, let's focus on the role of the surroundings and then temperature at which heat is transferred in the surroundings. So the surroundings are going to function as a heat source or a heat sink. That means the surroundings are going to absorb heat or release heat. In an exothermic process, the heat of the system is less than zero because we are releasing heat. Therefore, the heat of the surroundings is going to be greater than zero. And since we're going to have more heat, that's going to mean more freedom of motion. So the change in entropy of the surroundings is going to be greater than zero. And the surroundings are going to serve as a heat source since it's absorbing all the heat that's being released from the system. In contrast, the role of the surroundings can also be as a heat sink. So if Q of the system is going to be greater than zero this time, that means that it needs to absorb heat from the surroundings. So if it's taking heat from the surroundings, then Q of the surrounding is going to be less than zero. Okay? If Q of the surroundings is less than zero, then it's a heat sink because it's going to be giving away its heat to the system. If it's going to be giving away its heat to the system, that means it's going to be a reduction in the freedom of motion. If there's a reduction in the freedom of motion, then our delta S of the surroundings is going to be less than zero or fewer or decrease. We also see that the temperature at which heat is transferred affects delta S of the surroundings. Now we know that for any reaction, Q of the system is equal to negative Q of the surroundings. So that means the heat transferred is specific for that reaction and it's going to be the same regardless of the temperature of the surrounding. Let's consider the effects of an exothermic reaction at low or high temperatures. So at low temperatures, say 20 Kelvin, we see a decrease in microstates and therefore a decrease in entropy. But if we add heat, we see an increase in delta S of the surroundings. Remember, we're talking about an exothermic as far as Q of the system. So therefore, Q of the surroundings is going to have to compensate. If it's going to be releasing heat, then delta S of the surroundings is going to have to increase. And since it's at such a low temperature, that increase or adding any kind of heat energy is going to definitely allow us to disperse way more of the particles in the surroundings. And so that's the reason why we see that delta S increase or be greater than zero. You also can think of it as Q of the system is going to be negative or exothermic. Therefore, Q of the surroundings must be positive. So let's go further and talk about high temperatures. For example, 298 Kelvin. This is going to be a situation where we have an increase in microstates and therefore we already have an increase in entropy. So since the surroundings already have a large quantity of energy dispersed, there are more energy levels and the larger number of microstates, so transferring the same quantity of heat energy will result in a change that's relatively small. In other words, delta S of the surroundings is going to be greater when heat is added at a lower temperature. So if we're going to be adding heat, again, in exothermic processes that have low temperatures, we can see a greater increase in our delta S of the surrounding. Now, putting all these ideas together, we can say that delta S of the surroundings is directly related to an opposite change in the heat of the system, okay? And inversely related to the temperature at which the heat is transferred. In an expression, that simply means that delta S of the surroundings is equal to negative Q of the system divided by T. And for processes at constant pressure, the heat, which is now going to be QP, which is going to signify constant pressure, is equal to delta H, which again we know as our enthalpy. So now we can actually say that the delta S of the surroundings is equal to negative delta H of the system divided by T at constant pressure. So now we have effectively connected entropy and enthalpy concepts to one another. Another full circle moment. We also get a chance to see delta S of the surroundings and delta S of the system that we saw before. Now with delta S of the system, that's going to equal to the heat reversible divided by T, whereas delta S of the surrounding is equal to negative Q of the system divided by T, or negative delta H of the system divided by T at constant pressure. And I just want to make sure that I showed you what delta S of the system is as a reminder. So delta S of the system is equal to Q reversible divided by T. So you might be asked to find delta S of the surroundings if you're given delta S of the system. And then you might be asked to go further and find delta S of the universe, right? Or you might even have to find delta S of the system if you're given delta S of the surroundings, for example. You can even be asked to go further and calculate delta H of the system by using Hess's law and just taking the sum of the products minus the sum of the reactants, similar to what we saw before for a delta S in its standard state. And specifically, delta S of the reaction in its standard state. But the overall main point is still going to follow the second law of thermodynamics. In a spontaneous reaction, if we have a negative delta S of the system, meaning fewer microstates into which energy can be dispersed, then the delta S of the surroundings have to be positive enough for delta S of the universe to be positive and, of course, greater than zero. Why is this necessary? Because we need a positive delta S of the universe so that we can have a net increase in the number of microstates for dispersing the energy. So let's take what we know, start layering information, and use these new weapons at Dad's car. So we are back at Dad's car to gather weapons and use them for examples. Now that we have our understanding of delta S of the universe, we can predict whether a reaction occurs spontaneously in the direction of the product. So this tells us to determine the reaction spontaneity. At 298 Kelvin, the formation of ammonia has a negative delta S naught of the system. So we are at standard state here, folks, for the system. It gives us the reaction that N2 plus 3H2 is going to produce 2NH3. And delta S naught for the system is equal to negative 197 joules per Kelvin. It tells us to calculate delta S naught of the universe and state whether the reaction occurs spontaneously at this temperature. In other words, will the N2 and 3H2 molecules spontaneously form these 2NH3 molecules or not? Figuring out the delta S naught of the universe and getting that value will help us answer that question. But first, let's get our information together. For a reaction to occur spontaneously, delta S naught of the universe has to be greater than zero. That's something we know from the second law of thermodynamics. We also can say that delta S naught of the universe is equal to delta S naught of the system plus delta S naught of the surroundings, and that they all must be greater than zero. So we're given delta S naught of the system as negative 197 joules per Kelvin. Now, in order to solve for delta S naught of the surroundings, all we need to do is solve for negative delta H of the system divided by T. And if we want to focus on enthalpy in its standard state, we can simply say negative delta H naught of the reaction divided by T. And if we want to solve for negative delta H naught of the reaction, or simply delta H naught of the reaction, then all we need to do is take the sum of the number of moles of the delta H naught of formation of the products and subtract that by the sum of the number of moles of the delta H naught of the formation of the reactants. And these values will always be given to you either in the table or just be given to you in the actual problem itself. Once we have our delta H naught of the reaction value, and then we can use our temperature, we're able to get delta S naught of the surroundings. If we have our value for delta S naught of the surroundings, and we have our value for delta S naught of the system, we then can calculate our value for delta S naught of the universe, which is what the question wants. And then based on that value, we can state whether the reaction is going to occur spontaneously at this particular temperature. Now that we are in a full-blown calculation, I do want to add that the enthalpy units are different from our entropy units. So our enthalpy units are going to be kilojoules per mole. And therefore, to make sure that we can do a correct calculation and get delta S naught of the surroundings, we must make sure that we convert our kilojoules per mole to joules per mole. So let's go ahead and calculate our delta H naught of the reaction. For our products, we have 2 times NH3. And so we're going to get our delta H naught of formation, and that is negative 45.9 kilojoules per mole. This is going to be subtracted by our reactants. We have 1 times N2, and then we have 3 times H2. So for N2, our delta H of formation is simply 0 kilojoules per mole, and it's also 0 kilojoules per mole for H2. So therefore, our delta H naught of the reaction is simply going to be 2 times negative 45.9 kilojoules per mole, which is equal to negative 91.8 kilojoules per mole. Again, at this moment, we must convert kilojoules per mole to joules per mole. So we're going to go from negative 91.8 kilojoules per mole and multiply by 1,000 joules to get negative 9.18 times 10 to the 4th joules per mole. Now we're going to take our delta H naught of the reaction value and divide it by T to calculate our delta S naught of the surroundings. So it's going to be negative times negative 9.18 times 10 to the 4th joules per mole. We're going to divide that by 298 Kelvin, which is the temperature that's given. I get 308 joules per mole Kelvin. You also can see the units as joules per Kelvin, like we talked about. Now, to calculate the overall delta S naught of the universe, which is what the question wants, we're going to take our delta S naught of the system, which is given, which is negative 197 joules per Kelvin, and add it to the delta S naught of the surroundings we just calculated, which is 308 joules per Kelvin. And therefore, we're going to get 111 joules per Kelvin as our delta S naught of the universe. Since delta S naught of the universe is greater than 0, then this process is going to be spontaneous. And if it is going to be spontaneous, that means it's going to be spontaneous at this particular temperature, 298 Kelvin. Okay, folks? So we have effectively answered both portions of the question. We've calculated delta S naught of the universe, and we stated that this entire process of its reaction is going to be spontaneous at 298 Kelvin. So although the entropy of the system decreases, this is outweighed by the increase in the entropy of the surroundings, okay? This large increase in the entropy of the surroundings allowed delta S naught of the universe to now be positive, which is what we usually are looking for. We can also visualize this entire question in a graph. So if we know our delta S naught of the system is going to be negative because that was a given value, then on our y-axis, we have our entropy portion. And on our x-axis, we have our value for delta S naught of the system, the surroundings, and the universe. Again, delta S naught of the system was given, so it is red because it is negative value. It was given at negative 197 joules per Kelvin. Therefore, delta S of the surroundings, according to the second law of thermodynamics, had to be larger. And it had to be large enough to compensate for the negative delta S of the system. And as we can see, it was large enough. And we calculated it as 308 joules per mole Kelvin, or joules per Kelvin. And this offset of this increase in delta S of the surroundings allowed for delta S of the universe to therefore be a positive value and the entire process to be spontaneous at this temperature of 298 Kelvin. All right, folks, let's continue to our last concept of this portion of the lecture.